Hello and welcome to the Unit 8 Section 1 video on identifying quadratics. So this unit is going to be all about quadratic functions, and in this section we are going to talk about what is a quadratic function, what makes it quadratic, and then in the next sections that follow we're actually going to work some with quadratic functions. So we've got to start from the beginning. We have to be able to identify what is a quadratic, what makes a quadratic what it is. So quadratic equations. The function y equals x squared is shown in the graph here on the right. Notice that the graph is not linear. This function is a quadratic function. Okay? The shape of this graph is called a parabola, and it looks like a U. Now, there are three different forms of a quadratic equation. You have standard form, which is in the form y equals ax squared plus bx plus c. You have vertex form, which is y equals a times x minus h quantity squared plus k. And then you have intercept form, y equals a times the quantity x minus p times the quantity x minus q. So those are three different forms of quadratic equations. Now you'll notice that quadratics will always have an exponent of 2. So in vertex form, you've got an x squared term because you have this x here, and there is a square on the outside, so you're going to get an x squared out of this. In standard form, you just got the x squared term. It's just sitting there in the front. In intercept form, you have an x here, and you have an x here, and when you multiply those two x's together, your x squared term is going to come out of that, okay? So now that we've talked a little bit about how these equations are structured, let's see if we can identify which of these equations in example 1 are quadratic and which are not. So for A, we have an x squared term, and that is the highest power. So since we have an x squared term, A is quadratic. For B, we have an x squared term, but you notice we also have an x to the third term. And because we have a term with a higher power, it is not going to be quadratic. The highest power has to be 2. For C, we do not have an x squared term at all. With no x squared term, it's not going to be quadratic. For D, we have x minus 1 quantity squared. We will get an x squared term out of it, so D is quadratic. For E, we have a 2x squared, so an x squared term makes that one quadratic. For F, we have an x squared term, but you notice we also have a y squared term. You cannot have a y squared term. So since we have a y squared term, it's not going to be quadratic. In G, we have an x squared term on the end, but you notice we have x plus 1 to the third, and we're going to get an x to the third term out of it. So G is not quadratic. In H, there are no x squared terms, so it's not quadratic. For I, you have the 2x squared. There's your x squared term, so that one is not quadratic. Actually, that one is quadratic, okay? So we have to correct that one. That actually is quadratic because we do have an x squared term, and that's the highest power. So I is, in fact, quadratic. For J, we have an x squared term. We have two x terms, but those could be combined, so J is going to be quadratic. For Y, we have an x squared coming out of this, but over here we have another x that's going to get multiplied, so we'll end up with an x to the third, and so this one is not going to be quadratic. And then for L, we've got a 2x on the outside, you multiply by the x on the inside, that's going to give you your x squared term, so L is quadratic. Now let's talk about quadratic graphs. Let's see if we can figure out which graphs are going to be quadratic. Well, as we mentioned already, the graph of a quadratic function is a curve called a parabola. Parabolas can be oriented upward as shown earlier, or downward as shown to the right. Keep in mind that parabolas turned on their sides are not quadratic functions since they fail the vertical line test. In fact, they're not functions at all. If it's not a function, it's certainly not going to be a quadratic function. The graph of a quadratic function is the set of all solutions to a quadratic equation plotted in the coordinate plane. To graph a quadratic function, generate enough ordered pairs to see the shape of the parabola, then connect the points with a smooth curve. We're going to be doing more of this a little bit later in the unit. For now, let's see if we can determine which graphs are quadratic and which are not. So for A, this parabola is turned on its side and it fails the vertical line test, so it's not a function, so therefore it's not quadratic. For B, we have a parabola, so it is quadratic. C is not a curved line at all. It's not a U, it's a V, so this one's not quadratic. For D, we have just a straight line, so that certainly is not quadratic. E, it's a U, it's upside down, but it's still a U, so it's quadratic. F is a parabola, so that's quadratic. G is not a parabola, so it's not quadratic. H is a parabola, has that U shape, so it's quadratic. And then I, well, it's a circle, and it's certainly not a function because it fails the vertical line test, so it's not quadratic. Now let's talk about how to tell if a set of values in a table or in a set of ordered pairs is quadratic. So previously we've identified linear functions by finding a constant change in x corresponding to a constant change in y. The differences between y values for a constant change in x values is called the first differences. Okay, so you see that here. If we find the changes in y's, then we get our first differences. Well, now we're going to look at the second differences. So you find all your differences in the y, and then you're going to find the differences of those differences. If the differences of those first differences, so in other words, our second differences, if these are all the same number, then we are going to have a constant second difference, which means we have a quadratic function. So let's see how this works in an example. So in example 3, we've got a set of x values and a set of y values that go with them. The first thing we're going to do is we're going to check to make sure our x's are constant. So we have plus 2 to get to negative 4 to negative 2, it's plus 2. Then we add 2 again to get to 0, and then 2 again to get to 2, and then 2 again to get to 4. So our values on our x's are constant. So now we're going to go over to our y's. From 8 to 2, we subtract 6. From 2 to 0, we subtract 2. From 0 to 2, we add 2. And to get from 2 to 8, we add 6. Now we're going to check our second differences. Okay, so to check our second differences, to get from negative 6 to negative 2, we add 4. To get from negative 2 to positive 2, we add 4. To get from 2 to 6, we add 4. So we have a constant second differences because all of those second differences are positive 4. And so therefore, we have a quadratic. Let's take a look at B. So we check our x's first. From negative 2 to negative 1, we get plus 1. We add another 1 to get to 0, and another 1 to get to 1, and then another 1 to get to 2. So we're constant on the x's. Now let's check our first differences on our y's. So from 12 to 4, we subtract 8. From 4 to 0, we subtract 4. From 0 to 6, we add 6. And from 6 to 28, we add 22. Now let's check our second differences to see if that's constant. So negative 8 to negative 4, you add 4. Negative 4 to 6, you add 10. And already we see that we do not have constant second differences. So without constant second differences, we do not have a quadratic. Now, a set of ordered pairs is a set of x values with their corresponding y values, very similar to what we have in a table. If you're going to determine if a set of ordered pairs is quadratic, you need to write the ordered pairs in a table format and determine if the second difference is constant. So working with ordered pairs is going to be very much like working with a table. Okay? So you take your ordered pairs, you put them into the table, and then once you have them in the table, you check your x's, like we did before. Then you'd get your first differences of your y's. And then you're going to get your second difference from your first differences. So from 7 to 1 is -6. From 1 to 1 is 0. And then 1 to 7 is add 6. So the second differences are not constant, so this one is not a quadratic. For b, we check our x's. So we're adding 1 all the way along. We check our y's, so we get our differences in our y's, and then we check our second differences. And in this case, they're all -6. So we have constant second differences, and therefore you have a quadratic. All right, the last thing we're going to look at in this section is how do we tell if a situation is quadratic in a real-world scenario. So when presented with a real-world scenario, it is helpful to visualize what is being modeled. For example, a soccer player kicking a ball would be a quadratic since the shape of its flight path is a parabola, and you can see that here in this picture. Remember, this is just something I want you to keep in mind. Another way to write the output y is by using f of x, which is read as f is a function of x. So the height of the soccer ball would be a function of time, or h of t. H standing for height, t standing for time. You're going to see this quite a bit when you look at real-world scenarios, especially with quadratics, because we often use a quadratic to map a flight path of something, whether it be a soccer ball, perhaps a baseball, a football, maybe a rocket, or someone jumping. Okay, all of these things are examples of what we would have for a quadratic, because it follows the path of a parabola. So let's determine if each real-world scenario here would be modeled by a quadratic function. Drawing pictures is helpful when you're trying to think of what you're dealing with. So for A, the area of a square is a function of the length of the side of the square. Okay, so let's draw our square. The length of each side of the square is going to be x. So our input is the length of the side. Okay, we're going to put that in for our x. If we are getting the area of a square, well, the area of a square is side times side, which is x squared. So our output is going to be x squared here. So we could write a function for this. Our area as a function of the length, f of x, is equal to the length squared. Well, we do have a square in there, so therefore we do have a quadratic function. It takes a little bit of figuring in some of these. Let's try B. The height of a diver is a function of time. So let's draw our diving board. And let's draw our diver. So our diver goes off of the diving board, up into the air, and then starts to come down to the water. You can already see that shape of its flight path, of the diver's flight path. It looks very much like a parabola. So over time, the height of the diver increases to a maximum point, then falls until reaching the surface of the water, forming that parabola shape. So in this case, we do have a quadratic function. For C, the amount Jeremy tips at a restaurant is a function of the total bill. He tips 15% of the total bill. So our input here is the amount of the total bill. Our output is going to be the amount that Jeremy tips. So to get that, we have to put in our total bill, which is x, and multiply it by 0.15, which is 15%. This function does not contain an x squared, so therefore it is not quadratic. In D, Fernando hits a baseball upward from an initial height of 3 feet. The baseball hits the ground after 2 seconds. So let's model this. Here's Fernando hitting the baseball, and it does follow the path of a parabola. So over time, the height of the baseball increases to a maximum point. Then it falls until reaching the ground, forming that parabola shape. So therefore, we have a quadratic function. Rachel works at a hair salon. She makes a flat rate of $30 per day, and then she makes $15 per customer she sees that day. So we can say that what her input is the amount. Well, I forgot to change this. It's actually how much she is going to make. So let's not pay attention to all that information there because I forgot to change that out. What we have here is she makes a flat rate of $30 per day. So that's $30 plus 15 per customer. So that's 15 times X, where X is the number of customers she sees per day. So this one is not going to be quadratic, but it's not going to be quadratic because there's no X squared in the function. So similar to what we had there in the previous example. And then finally, the distance a ball travels after being dropped is a function of acceleration and time. The distance is 1/2 of the acceleration multiplied by the square of the time. Well, interpreting the problem, the function of distance is 1/2 acceleration times time squared. Okay? Just kind of read what they told you. All I did was I put into mathematical format this sentence as to what they described it as being. There is a t squared term, so therefore this is a quadratic function. All right, that finishes off this first section on quadratics. You should be able to identify quadratics now and be able to determine if it's quadratic based on an equation, a graph, a table, a set of ordered pairs, or in a real-world scenario. So in the next section, what we're going to do is delve a little bit deeper into looking at a quadratic function, and more specifically, a graph of a quadratic. And we're going to determine some of the key features of that graph.